Today we're going to study right triangle trigonometry. When you have a right triangle, you can use the SOHCAHTOA rule that you've learned earlier to find the sine, cosine, or tangent of a particular angle in the right triangle. For instance, in the example below, we have a right triangle where we have side lengths 3, 4, and 5. Angles alpha and beta are labeled. So we're asked to find the sine, cosine, and tangent of alpha. So with respect to angle alpha, the 4 side is opposite and the 5 is the hypotenuse. And so we have the sine of alpha is 4/5. I don't know if you can see that, but a new version of Java is ready to be installed. So I will dismiss that, and we'll keep going. With respect to angle alpha, side 3 is the adjacent side. Adjacent side, remember, means next to. And so this side is next to alpha, and of course that side was opposite of it. So we've got 3/5. Tangent is opposite over adjacent, and so we have 4/3. For side beta, with respect to side beta, 3 is opposite and 5 is the hypotenuse, so sine of beta is 3/5. Cosine of beta is the adjacent side over the hypotenuse, and then we have opposite over adjacent. Next up are the cofunction identities. Yesterday, or in the last lesson, we studied the Pythagorean identity, one of the most basic trigonometric identities. The cofunction identities are identities because they have an equal sign, meaning one side is equal to the other. In a sense, they're identical. They have identical values. What this is saying is that the cosine of an angle is equal to the sine of 90 degrees minus that angle. In other words, suppose that our angle theta were 30 degrees. Suppose it was 30 degrees. Then 90 minus 30 degrees would be 60 degrees. So what this cofunction identity is saying is that the cosine of 30 degrees equals the sine of 60 degrees. Or the cosine of 80 degrees equals the sine of 10 degrees. Essentially, this is a rule that tells us something about complementary angles, two angles that add up to 90 degrees. The second identity tells us that the sine of an angle is equal to the cosine of its complementary angle. We can use this property at different times. So, for instance, suppose that we knew what the sine of 22 degrees was. Then we would also know what the cosine of its complement was. 90 minus 22, which is 68. Just as an example. Going down below, suppose that we have a right triangle that has an angle of pi/3. Think of a 60-degree angle. And has a hypotenuse of 20 centimeters. Find all the unknown sides and angles. So let's set up a right triangle. Boom. This right triangle has a 60-degree angle in it. Since we know two sides, we can figure out the third side, and so that of course must be a 30-degree angle up there. It's got a hypotenuse of 20 centimeters, so the side across from the right angle is 20 centimeters. We need to find all the unknown sides and angles. Let's use some right triangle trigonometry to help us. Now, I know this angle here is 60 degrees, and I also know one of the sides. I don't know what this side opposite 60 degrees is. So, let's think about it this way. The sine of 60 degrees will equal the opposite over hypotenuse. So that equals y over 20. Now what we can do is we can think of what is the sine of 60 degrees. Ultimately, we want to find out what the side y is, but we want to put a number in place of this sine of 60 degrees. So think of basic 60-degree angle. Got a 60 here. That is very hard to see, but you know what I mean. So for a 30, 60, 90 triangle, this would be 1, this would be root 3, and the hypotenuse would be 2. And so the sine would be opposite over hypotenuse, or root 3 over 2. Equals y over 20. At this point, we can use cross products and then solve for y. So 2 times y, and then 20 times root 3. Last, divide both sides by 2, and we would have y equals 10 root 3. So this side is 10 root 3. Last side, we could do a couple different ways. For the last side, what I want to do is find this side here. I'm going to call it x because it's a horizontal distance. So we can use right triangle trigonometry again and use the sine of 30 degrees this time. I can use sine of 30 because I want to know the opposite side and I know the hypotenuse. To do it this way, I only have one unknown. That's my side opposite. So now for the sine of 30 degrees, I look at this reference triangle again and I see that this is the 30-degree angle, and then sine is opposite over hypotenuse. So that's 1/2. It's x over 20. So if 1/2 equals x over 20, then I know that my x must be 10, because 10 over 20 simplifies down to 1/2. So x is 10. So this number here is 10, and this number was 10 root 3. Scrolling down a bit. We're asked to use a calculator to find the trigonometric values and angles depending on the circumstance. You must be aware of the mode that your calculator is in. So for this problem here, I see that I'm being asked the sine of an angle in degree measurement. So go to mode on your calculator and then make sure that you are in degrees mode rather than radians mode. The second thing that we need to do is we need to change this angle. Not really change the angle, but change the way that it's represented. So right now the angle says 32 degrees, 35 minutes. Now remember from a previous lesson that a minute, this little symbol here, a minute represents 1/60th of a degree. And so 35 minutes would represent 35 60ths of a degree. So let's think about this angle as the sine of 32 and 35 60ths degrees. Now how do we enter that in your calculator? We can do it in more than one way. One of the ways is this. Press the sine button, and then it's going to pop up that parentheses after the word sine. The sine of 32 plus 35 60ths. This is one way that you can represent a mixed number on your calculator, such as the one that we have here. So enter that in, and the output, let's put this to 4 decimal places, is 0.5385. Do the same sort of thing with the second one here. Do the tangent of 77 plus 18 60ths, and your calculator is going to give an output of rounded to the nearest. Oops, let us erase that. Rounded to the nearest 4 decimal places. 4.4373. Alright, for these bottom two, we're given the trig value, and we're supposed to, in a sense, work backwards to find the angle. To do this with your calculator, you'll want to use the cosine inverse feature. What the cosine inverse function, or the cosine inverse feature does, is it undoes what cosine does. So if we do cosine inverse to both sides of our equation, cosine inverse to both sides, then that's going to undo this cosine here. Cosine inverse undoes cosine, and we're left with theta on the left side of our equation. So on your calculator, what you'll do is you'll enter cosine inverse of 0.5678. When you do that, you're going to be given an output of 55. That does not look like a 4. Let's change that. 55.40304489 and so forth. And so this is an angle in degrees if you've got your calculator in degree mode. Now let's change this into degrees and minutes. Here's how I would do that. Take what your calculator is showing to you and subtract 55 from it. That's going to leave you with just this decimal part, 0.403 and so forth. Then take that decimal and multiply it by 60, and that's going to give you your number of minutes. After doing all that, you'll have an angle of 55 degrees and, rounded to the nearest minute, 24 minutes. Do the same sort of thing with this last one on the page. So to undo tangent, we need to use tangent inverse on both sides. Tangent inverse undoes tangent. We're left with theta by itself on the left side. Do the tangent inverse of 5.7, and we have 80.0497, and it goes on from there. Subtract 80 from that, multiply it by 60. It does not look right on my screen. Alright, sorry about the delay here. Subtract 80, multiply it by 60, and we'll be left with theta equals, yikes. I apologize for this. The old computer's just working a little slowly. It's not quite catching up. We have 80 degrees, and rounded to the nearest minute, 3 minutes. So I'm going to end this video here, and I'll pick this up with a new video to do